See if this goes.
All right. Yep.
I don't know, that's a good thing I did this too. Because every time I'm not, I'll be honest, like I'm new, like, I'm not the greatest with this technology
This
stuff.
goes.
So
All right.
okay, I think it is live. So
It is live.
I will let this sit for a second, so that way, um, because we get a lot of people from down under that likes to join
Oh,
our
yeah.
chats. So, but sometimes he doesn't see it till like it goes on for like 5 minutes and then like it'll push through. So I figure I'll just let it run for a little bit.
Yeah, 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 yeah.
However that technology works or the
Yeah,
algorithm.
we actually run formal talks this way at the Royal Astronomical Society. So
Okay.
yeah, yes,
Yeah, it's just easier just to start it and then at the time of like, hey, we're here. Now we're
yeah,
gonna start. So, but we're pretty informal as you can tell. I mean, it's hard for me to be formal when I'm on the road 90% of the time, it seems like. So I got to do everything from this laptop.
yeah,
It's nice at home because I got the dual screens, I get set up, stuff on the side, but here I just got
yeah.
a laptop, but it works.
One of the things I noticed a lot in lockdown time in COVID
Mhm.
was we had a lot of Zoom and
Yeah.
Teams meetings. Um, but I can't read the room in the same way that I do
Mm.
for a real meeting. I
Yeah.
can't get the sense of what the room is thinking in the same way. And yeah, yeah.
Yeah,
And
that's
also
the
jokes, you have
downside.
to be very careful about. We had one, and they had an owl which took everybody around the table and spread them out in a line, and the in the middle was the president, and he had a shock of white hair, and the sun was behind him, so it looked like a halo. And I said, "You guys look like the Last Supper. You really do." And it went down like a lead balloon. Nobody laughed at all. And eventually, Mike, the president, rescued me by saying, "Okay, so which one's Judas?"
Oh,
But but it was just nobody laughed. I thought, oh, okay, it's really funny. But of
yeah,
course, he couldn't see what I could see.
yeah, right. So it's like it's not quite the same. All right, cool. We got a couple people in so far, so it's good. That means the link is out, so we'll
Uh-huh.
we'll let it we'll start it a little bit after 5 maybe. Well, 5 our time. My time. Tanya, you're for 4 o'clock.
Yeah.
It's weird as
Well,
else. I don't time is irrelevant. I
we'll
don't
start. We'll
know.
start at yeah. We'll start
Don't
at a little bit after hour. you shouldn't
yeah,
tell a Put it this way. speaker who's very could easily overrun that that's the case.
I know.
I
Like,
I generally go at a slide a minute, by the way. So
okay.
uh, That's uh, perfect. I have 48, so and some of them are not don't need a minute. So
Okay.
I should be about 45 minutes is the plan, but
Okay.
we'll see.
We'll see. We'll see how it goes. I'm gonna put this in the other chit chat too while I'm sitting here. Let's see if I can share the link. Copy link.
Oh, in Space Weather Unplugged.
What's that?
Space Weather Unplugged,
I
the
know
website, the
uh
hour.
the what chat am I in? The Twitter chat, the Twitter one.
Oh yeah, perfect.
There, yeah. I know it's funny because it's funny. Some people ask me like, "Don't you edit your videos?" And I'm like, "No." Like because like stuff like this, like cut all the beginning stuff, and I'm like, you can fast forward through it. I'm so bad.
No, no, life's too short.
Yeah, like it's all good.
Yeah.
So anyway, okay, all right. See what we got here. Da-da-da. I like having it up on the. See, this is where having the dual screen is nice because then I can monitor the chat instead of having this on my phone.
Yeah.
But because sometimes people, well, because although we've had some pretty good discussions in the chat on these, like people just
Hmm.
kind of ask
Yeah,
questions.
and actually, if something
So,
comes up that doesn't, it feels like it needs explaining now rather than at the end,
yeah,
then by all means say something in the chat's asking.
Okay.
why? Or is that really right? Or,
Yeah.
I don't mind that. That'd be fine.
Explain this further.
Yes, yes, yes.
Like in
And
less than
laugh.
an hour. Like, that's always the fun part, right? Okay. Oh, let's see. It's 5:01. So let's do this. So I think we can start it. So I will introduce you. Um, I'm just gonna go off of what we wrote because I'm not that creative. So, but anyway, so we have a special guest today for those who are joining on our lovely little podcast slash YouTube channel. Um, with us today, we have Professor Mike Lockwood from the Royal Astronomical Society in the Department of Meteorology. But you're a professor of space environment physics, right? Did I get that right?
Right.
All
That's
right.
right.
Just making sure I'm reading the thing right. And then your research interests include magnetic fields of the sun, interplanetary space, the Earth, and general solar influence on global and regional climate. And you've been published in hundreds of papers. So this should be pretty fun to pick
I'm
your
not going
brain
to
with.
talk about them all, don't worry.
Yeah. Um, we've been really looking forward to this because I think the magnetosphere is one of the kind of I mean, amongst anything in physics, kind of misunderstood, and there's a lot of like correlations people have made, and it doesn't quite translate. Like for example, like looking at this solar wind data coming in, and the biggest thing you'll see online is like, well, why was there aurora when it was a positive BZ? You know, kind of stuff like that. So,
Yeah.
and I've in the year or so that I've been doing this and learning from, wonderful people like you, is like, oh, there's a lot more to this than what meets the eye. And it's been pretty fascinating. And yeah, so we've been super excited about this, to say the least. So I will hand it over and let you take the stage.
Shall I start? Okay, so I
Yeah,
press this green button here.
yeah, press that green button. Should bring it up. We did test
Okay,
it.
there we go. And I go to presentation mode.
Rock on.
Come on. There we go.
Okay.
Right. Well,
Hey.
good good evening, everybody. Afternoon, morning, wherever you are. Um, I'm Mike Lockwood, and I was asked by Mary Beth and Tanya to talk about aurora and substorms, but in particular to try and understand why the equinoxes are important and
Yes.
something called
Yep.
the Russell-McFerran effect. So that's my brief. So that's what I'm going to do. Okay, so let's move on here. This is a very old movie. It was made by Dynamics Explorer back in 1997, and it shows back then the sensitivity wasn't so great. Aurora is present as a ring around the poles all the time, but sometimes back then it was so dim that we couldn't see it. And this movie starts off in that situation. There's a little timeline here on the right. So you have some magnetic indices of showing you magnetic disturbance on Earth, and these red spikes here are what we call substorms. This is the solar wind velocity, and in this period it picks up and then decays away. The magnetic field picks up and it swings around between south and north before deciding to stay south for a long time. Okay, and that's what these show. So if I run the movie, we just watch what happens. It's a bit like a roller coaster ride. We're moving, and so the stars move. Notice the aurora oval expanding there. That was a substorm. Okay. Now, actually, things are not happening at the same time. The pointer is supposed to move over, so that's not working. Oh well, it doesn't matter. Um, and now we're looking at the other pole, and there's still a few smaller substorms coming on because we're over here towards the end of the whole period. Okay. So rather than actually run that again, I've broken it out into some frames. Oh, there we go. It's decided to move across now. So here we are at the start. Okay, before things get going. We're getting a little bit of brightening of the aurora because of the increase in the solar wind velocity. In other words, a shock front has hit our magnetosphere and that's made the aurora brighten up. But it's still northward IMF here. If you look, this is the southward component of the IMF in a frame that matters. And if I roll on to the next snapshot, here we've had a period of southward IMF and you'll see the polar cap, the ring has expanded. Okay, so that's me bringing aurora to lower latitudes. Just that short period of southward IMF has caused it to expand quite a lot. It goes northward again then and messes around a bit, but we do actually get a little bit of a substorm forming here. This is this guy here starting, okay, but it's quite a small one, okay, and then it develops, okay. Now we come around and we flipped to the other hemisphere, and I've jumped onto here, and this is this substorm here, and you can see this very thick band of aurora on around midnight on the night side. By the way, this is in ultraviolet, so it's what a bee, if you took a bee up into space, this is what aurora would look like to a bee because they see in ultraviolet light. And then as things go on, we continue to, this is what we call the recovery phase of a substorm, where it's all the aurora's kind of breaking up and things quieten down as we go on. So that's what a substorm is. Just to say, you probably know what aurora is, but I'll just go over it. You have all these different gases in the upper atmosphere. This is the what we call the thermosphere, above about 200 kilometers altitude. And if we've got the magnetic field there, we get an energetic particle coming down, and there'll be an atom in its way or a molecule. And it hits it, it causes it to get excited. Sometime later, what we call the delay time, then it emits a photon. It may emit it down or it may emit it upward. Okay, and that was a green one because that was quite an energetic particle that got all the way down and hit an oxygen atom low down. If we have a field line where in the way is an atom that's higher up, then same thing happens. It excites after a delay, and in this case it's a very long delay, then it emits a red photon. So we get red from higher altitudes than low. The reason we don't see red lower down is it actually takes nearly 2 minutes for this excited atom to de-excite and emit a photon on average. And in that time, it's likely, if it's low down, it's going to collide with something else. And so the red line doesn't crop up low down. It gets what we call quenched. But from higher up, then it's got to, before it collides, it's likely to emit. And we do see red from higher up. So, and there's a whole series of different molecules and atoms that can give us, this is the green line of oxygen from lower down. There's lots of different red lines. These are nitrogen lines over here. So there's lots of different colors that we can get. There's even an orange and things. So you do get orange in aurora. So how's this happening? Well, it's all to do with the solar wind. Now, something that is often said that is wrong is that the particles in the aurora come from the solar wind. That may be true in the quietest times to some extent, but as soon as things get active, it's not true. In fact, most of the particles are coming from our ionosphere, but the energy always comes from the solar wind. So we have solar wind blowing up, pressing the magnetic field on the day side, squashing the magnetosphere, and dragging the tail out on the anti-sunward side. And with that, oh, I've gone the wrong way. With that comes a magnetic field. And because it's supersonic flow, the first thing that happens is there's a bow shock that slows the flow down. And so the field line is slowed to start with here at the nose, but out here it's carrying on at the same speed. And so increasingly the field gets draped over the nose of the magnetosphere, okay, because of this slowing behind the shock. And eventually, if the field is southward, like I've drawn here, in a frame relative to the Earth's magnetic field. Earth's field is northward. We have this anti-parallel field, and the most interesting process in space physics, which is magnetic reconnection, which in my career, we've come a long way in understanding, can take place. And instead of the field lines being anti-parallel on the two sides of the boundary, they interconnect across the boundary, and that allows particles in. Now, those particles are solar wind particles. They'll be low energy, and you'll only get red aurora. We'll have some coming in from the other hemisphere as well. And that's called the cusp aurora. And those are solar wind particles, okay? Some other particles, they get in. Now, these trajectories aren't field aligned because although the particles are coming in down the field lines are moving, so the trajectories are not field aligned. And they end up here in the night side of the tail, where energy that's been extracted and stored in the tail can be released, and then in doing that, they're accelerated back to Earth, and we get green aurora. They're more energetic particles, penetrate lower, and excite the green line, and the red line's quenched out, so it's green aurora. Now that does happen, but when we look at the composition of the ions that go with those electrons, we find that actually only during very quiet times are they actually from the solar wind. And that most of the time what is happening is ions and electrons from the ionosphere here are coming up. Again, they're coming up the field lines, but the field lines are moving, and they end up giving us the green aurora. Okay, so the statement that aurora is particles from the solar wind is actually more wrong than right, but the energy always comes from the solar wind. The energy that excites them and accelerates them back to Earth comes from the solar wind. Now, don't worry about this. It's much simpler than it looks. There's a way of calculating how much power is being inputted into the magnetosphere. It's the power density that the solar wind has, which is largely in the kinetic energy of the particles. We can calculate that. We present a certain area, the cross-sectional area, so the area of the magnetosphere as seen from the sun, we present that, and then a certain fraction of the energy that's incident on that area comes into the magnetosphere, and that fraction is actually quite low. It's about 2% actually, so it's really very low. Most of the energy goes around the flanks and carries on down in the solar wind, but we do extract about 2% under southward IMF conditions, under optimum conditions. We can calculate all those three terms, put them together, and we get an expression for this. And we can calculate this on a regular basis from our measurements in interplanetary space. One of the key things to notice is this funny thing here, this angle, which is essentially this is 1 for a purely southward field and it's north for a purely northward field. Okay, so this is key to that, how much we have that anti-parallel field that allows the energy transfer into the magnetosphere. So it looks like a horrible equation, but actually it's really quite simple, and but it's very useful. So that's the power input into the magnetosphere, which is kind of half the story. Just to say, one of the things that we need to have in this is the magnetic field moment of the Earth, and that's not constant, it's changed. And not only has the field magnitude changed, but the poles keep moving around. This is where the poles have been. I think the blue is 1650 and the red is now. So that's where the North Pole has meandered around. This actually makes a difference to where aurora happens, because aurora comes down certain magnetic latitudes. During quiet times, it would be these ones here, moderately disturbed these, and very disturbed, it'd get right down, maybe, not really, wouldn't really get that low. But you'll notice that where you are in America, the change hasn't made much difference to your magnetic latitudes, particularly over this side on the west coast. But on the east coast here, it's made more difference, and it's made a lot of difference over Europe. And so the movement has changed where we see aurora. And just to put it in context, this is some locations around the British Isles. So this is for us. So this is Plymouth. Now in 1650, Plymouth was a great place to see aurora. You were right bang in the auroral oval. It was like Tromsø or something nowadays. Um, but as the pole went away from us, then you had to go further and further north to see the aurora. But places that were too far north to see the aurora on a regular basis, this is the occurrence distribution of aurora in magnetic latitude, they started to come southward in magnetic latitude. And so now we do see the aurora in the Faroe Isles and in Shetlands and things. So it's quite interesting how aurora has sort of over the centuries marched northward for us, and it's very rare in the south of England, but quite common now in the Faroe Isles. Right. So, and then this is just a survey we did where of it was nearly 250,000 sightings of aurora, and it goes right back to 1650. There weren't many. This is so-called Maunder minimum when there weren't any sunspots. And then you see where aurora is. There's some locations here. This is in magnetic latitude, and these are locations of various sites and how they've changed over time. The ones in America haven't changed as much as the ones in Europe, as I've already said. But you'll notice these are the solar cycles, grey, white, even and odd numbered solar cycles. And you'll see it at sunspot maximum, we do tend to get these very large events. Okay, this is actually the Carrington event here, famous event. This is actually the most extensive auroral event ever, which was 4th of February 1872, believe it or not. And then the very last one here was May 10th of last year. Okay, right at the end of the plot here. So you can see it's a really exceptional event, really unusual. In fact, probably the third most extensive in terms of where it was observed. Right, so just to move on a little bit, and this is helping a bit. This is the variation over the last solar cycle. This is sunspot number here, sunspot minimum, maxima here and here. You can see the aurora retreats back northward on average, but there's this strange thing. You'll see the peaks here are cropping up around the equinoxes. Now, we tend not to see it in the middle of each year. This is the summer solstice for the Northern Hemisphere. This is all Northern Hemisphere data, by the way. Um, because of sunlight, basically, it inhibits it. And so if I look at the occurrence probability, this is all that data going right back to 1650. This is the occurrence distribution of aurora at certain latitudes. So this is anywhere in yellow, and you'll see it piles up at the equinoxes. And then this is right down at very low latitudes, below 50 degrees geomagnetic. And it's very rare, so there aren't many samples, but it's still piling up at the equinoxes. And you'll see we don't have many here because it's summer, and this is the effect of sunlight. Well, it's partially the effect of sunlight. There is another effect. So aurora is definitely more common at the equinoxes. And that's not at any latitude. And that's not so surprising because we actually know the same is true of geomagnetic activity. So this is sunspot number here, going back to 1868, when a particular geomagnetic index that I like, I've done some corrections on it, but this is a corrected version. This is the actual index. It's plotted as a function of the fraction of year here. So this is January the 1st, this is December 31st at the top, and year along here. And you'll see that the equinoxes are where strong geomagnetic activity is cropping up. And this is the same data, but it's been normalized to the average value of the year. And you'll see these consistent peaks along at the equinoxes. And this is actually, this is the occurrence of very large events as well. It goes up with the solar cycle. So we've got more here because sunspot activity was higher. But again, largest events are tending to crop up at the equinoxes. And we call this the semi-annual variation because there are two peaks in a year, one at each equinox. So, how do we explain this? Well, the first thing I've got to do is get you used to something called that I call FUT plots, time of day, time of year plots. So, time of day is the universal time, okay, and time of year is the fraction of the year that we've gone through. And if I plot something as a function in color, as a function of those two, I get patterns like this. And this is actually the pattern of this angle here between Earth's magnetic axis and a northward pointing axis in the solar frame. This is the best solar frame to be using. It's the one the IMF is most ordered in. And this angle delta, it varies with the time of year because the rotation axis, as the Earth goes around the sun, then this precesses around this northward axis here. So it's got a time of year variation. And then every day, as the Earth rotates, this magnetic axis, which is offset from the rotational axis, the magnetic pole is separated from the rotational pole, and so the magnetic axis precesses around the rotational axis, and so we also have a time of day variation. And the net pattern for this angle here looks like this, okay? And this angle here is a maximum. This is actually the tilt towards the Earth. Okay, it's towards the sun rather. X is towards the sun in this picture. And so you get the maximum delta, the tilt towards the sun for June solstice here in the so the summer solstice, and it happens to be with at about 16 UT. Okay, and the maximum tilt away is for summer in the southern hemisphere, and that's down here. Okay, so the minimum delta, as defined positive toward this way, is 4 UT at the December solstice. So that's the pattern of the tilt towards and away from the sun. I'll come back to that because it does have an effect. But then what's this Russell-McFerran effect? Now we're looking slightly differently. We're looking at the Earth from the sun. So instead of the X direction being off to the left, X points from the middle of the Earth to the middle of the sun, and the X direction is therefore coming at us. And we define Z and Y this way. And now we have the magnetic axis, and it's making an angle alpha in this ZY plane, and that varies over the year as well because of the two tilts. And we get this strange pattern out of that. Now, I'll explain why in a bit, but it has this peak here, maximum near 22 at the March equinox, and another maximum at 10 UT at the September equinox. I'll explain why that is in a moment. So there are these two patterns that just arise naturally out of A, the Earth moving around the sun, and B, the Earth spinning and having an offset magnetic axis relative to the rotational axis. Now, these FUT plots, you've got to be careful here because if you use a geomagnetic index that isn't made from a nice homogeneous network of stations, they imprint a pattern onto it. For example, if it's daytime, you've just got one station, it's going to see more geomagnetic activity in daytime because the ionosphere is more enhanced and so you get more currents, the conductivity is higher. And that index I showed you before just was made from just two stations, which is why it can go all the way back to 1868, one in southern England and one in Australia. And when you look at the inherent response that will give you, you can model that on one of these FUT plots. It's horrible. Okay, this is summer for the northern hemisphere station, and this is summer for the southern hemisphere station, and you get this really weird pattern. It's it's very bad at low activity. It's not quite so bad at high activity, but it's still pretty horrible. Okay. The index you should use is AM, not AP for sure, AM. AM has a ring of stations all the way around. There are obviously oceans that get in the way. particularly here in the southern hemisphere ring, but it's got one in both hemispheres, and it's as even a distribution. And in fact, the way we average things to put this together, we use weighting functions to allow for the fact that we've got gaps in the ring. And when you look at its response function, there's a little bit of variation in here, and at high activity, it's almost completely uniform. It's a lovely index. It's not imprinting onto the response something to do with just where the stations are. The one you shouldn't use, unfortunately, is used a lot of the time, but it's a horrible index in my book, is KP. Because KP has it's very Eurocentric. It has a few American stations and just two in the southern hemisphere. And to make it worse, the way it's compiled is every station is mapped back to what Potsdam would have seen at the same time. So it very much imprints the pattern that you would have for Potsdam onto the index. Okay. So it's not a good index in this context of looking at the time of day, time of year. But AM is, it's got this nice flat response function across the parameter space we're interested in. Right, so don't use AP if you're interested in the Russell-McFerrin effect. It's going to lie to you. Right, so there are three potential explanations of the patterns of patterns in these FUT plots. The first is called the axial effect. The second is called the Macintosh or equinoctial effect. And the third is called the Russell-McFerrin effect. Okay, and spoiler alert, the bottom one's the most important one, although the second one does come into it in a way we hadn't expected. If you look at how Earth moves around the sun, you find that relative to the Earth, the ecliptic plane in which our planet moves is inclined relative to the magnetic equator of the sun by about 7 degrees. So we actually go and we're 7 degrees above the magnetic equator of the sun near the March equinox and 7 degrees below at the other. Now, if there were something that varies with that latitude, then it wouldn't matter about UT, it wouldn't matter what direction where the Earth was in its daily spin, but it would matter where it was in the time of year. And you get this vertical structure on these FUT plots. We call this an axial pattern, okay? And for a long time, it was thought that this was the cause of the semi-annual variation because you have these two peaks. And it was thought that what was happening was that you were more likely to intercept fast solar wind if you were away from the magnetic equator. And that's true, although it's not a very great effect. It's true at sunspot minimum, where we have these big polar coronal holes, but the streamer belt is quite narrow. So if Earth is moving through the edges of the streamer belt, you would see a gradient. But you come to sunspot maximum and you've got streamer belts at all latitudes. You've got fast solar wind catching up slow solar wind, so both move at a sort of average speed. You've got much less structure, so it's not going to work at sunspot maximum. So the axial effect had questions about it anyway. Okay, let's not worry about that. Okay, let's come on to the second one, the Macintosh effect. Now, if I take the angle between the direction to the sun and the magnetic axis, let's call this psi here, and plot that, or the cosine of it, I get this characteristic sort of hourglass pattern, okay? And this just arises from the two precessions that I talked about, okay? So that's characteristic of this angle, okay? So it includes the tip towards the sun and away from the sun, as well as the tip from side to side. And that's what this is showing here, okay? So this characteristic pattern, okay, this is actually calculated for a given year. Right, and then the last one is the one I'm interested in, and this is the Russell-McFerrin effect. And it's the same two precessions, but now we're only interested in how those axes are moving when projected onto the ZY plane. We're not worrying about the tip towards or away from the Earth. And why would we worry about that? And how does it give this strange pattern? We call this the characteristic Russell-McFerran pattern. Okay, so that I can't avoid explaining anymore. Before I do explain it, one of the things that was hoped could differentiate it is there are slight differences between the times of year that these things crop up, these peaks crop up, but they're very slight and it's not enough for it to let you differentiate which pattern is happening on average. Um, now, um, I've said that we favor the Ross-McFerran pattern. So the next slide is going to be a bit of a shock because when you look at that ideal index, the AM index here, this is the best one, then you find not a Russell-McFerran pattern, but an equinoctial pattern. Okay. And a lot of people, they tried to modify the Russell-McFerran effect or just decided it didn't really work because they were getting this equinoctial pattern and not the characteristic Russell-McFerran pattern. Okay, so I have to explain why that is. There is an explanation, but okay. So why is it that we're so certain that the Russell-McFerran effect is important? So let's just take, here we are, X is towards us. We're looking from the sun to the Earth. Z northward in a solar frame, Y in this direction. That's a right-hand set. Um, Incidentally, I've been a bit dry so far. I've got to tell you a little story. This is a story about Catherine McWilliams, who was a dear colleague of ours who died at a horribly young age. She was only 50 something, 53, I think, this earlier this year. And at her funeral, her brother was saying that he taught at the same university as her in Saskatoon. And he said that he noticed that students were going by and giving her this strange greeting like this. And then, even more worrying, was she would reply with it. And he thought, is she forming some kind of cult here? And this is some kind of salute. And so she eventually explained that it was the right hand rule for, so when you do a right hand coordinate system, X to Y has to give you Z according to the right hand rule. Okay, so, and so that they would learn it, she said, whenever you see me, you're to greet me with the right hand rule. And if you do it wrong and use your left hand, you're going to lose marks and things like this. So it was a rather nice story that her way of teaching the right-hand rule to people. Anyway, these are right-handed sets. X to Y gives you Z according to the right-hand rule. So if we were at March equinox, particularly around about 22 UT, then Earth's magnetic field is tipped over like this in this frame as we look from the sun. Okay. So if we have a large negative By in the solar frame, that will map to a southward IMF, and that's good for connecting to the energy of the solar wind and giving us aurora. Okay. On the other hand, if it's tipped over this way, which it would be in the September equinox, particularly at about 10 UT, then it's a positive By that gives us southward IMF. So there's a major prediction here of the Russell-McFerran effect that we expect under average conditions By positive to give us good aurora at the September equinox around about 10 UT and at March equinox around about 22 UT. And that is exactly what we find. I'll show you that in a moment. But there's a thing that people got to remember here is that those FUT patterns are the averages over several years. Okay, so we're talking about average behavior to get these patterns. So what happens on average during major events rather, And what we find is that it's not BY that's driving things, it's actually BZ in the solar frame. So this vector here is pointing down southward, and that gives us a southward IMF in the magnetospheric frame. And I can show you that. So here is a plot of BZ in Earth's magnetic frame against BZ in the solar frame. And you'll see that they run pretty much along a 45-degree line. Okay. So these really large southward IMFs here in the magnetospheric frame are being driven by large southward field that the sun is throwing at us. Okay. And the Russell-McFerrin effect is just giving us this broadening here, okay? But it affects the average of things. What I've done here is this is all data. This plot here is just for very large geomagnetic activity, the top 1% of, and you see that we're in this quadrant here, and it's large southward field in the solar frame, giving large southward field in the magnetospheric frame, giving us geomagnetic activity. So big events are not caused by the Russell-McFerrin effect. They're caused by field that is actually pointing southward already. It doesn't need the tipping over to turn BY in a solar field into southward field. Okay. But one of the things is that BY is pretty symmetric. This is, well, 4 solar cycles worth of data, and the BY component is fairly symmetric. So positive is as common as negative. And if we look at a geomagnetic index, what I've done here is I've plotted the variation. Here's the semi-annual variation with peaks at the equinoxes, but then I've separated it into periods where the BY was positive in the solar frame and the BY was negative. And in the positive one is the open circles, and look, it's peaking in September, and the negative one is, and it's peaking in March. Okay. And this is the occurrence of large events, and that's sort of doing the, or moderately large events that's doing the same thing. So this is a unique prediction of the Russell-McFerrin effect, that the IMF-BY in the solar frame is having this effect, giving us a semi-annual variation, but it's one or the other depending on the BY. Okay, so, but it's an average effect. It's all those big storms caused by large southward field in the solar frame are actually being averaged out, and this is what's left, this systematic variation. And here it is. So this is proof of what I'm saying. This is, in fact, the power input to the magnetosphere calculated from that equation I gave you. This is By negative, this is By positive, and there it is. There's the Russell-McFerrin pattern. There's the March peak up here at 22 UT. Here's the September peak. This is the model, and this is the data. And so the Russell-McFerrin effect is these two put together, because we get 50% positive BY and 50% negative BY. Okay. So when you split something by the two polarities of BY, that's what tells you that it really is Russell-McFerrin doing it. Okay. And when we split geomagnetic indices, we find that it's either goes September or March. So at the core of all this, at the core of the energy transfer into the magnetosphere, is the Russell-McFerrin effect. And that's what I'm showing here. This is, I think, yes, this is the AM index. And so you've got a peak here. Okay, it's getting a little bit wiggly. It's getting a bit equinoctial, but it's all September for March, for positive BY. This is negative BY, and it's all March. Okay, so the indices are actually telling us, yeah, the Russell-McFerrin is working. It's got a little bit of a equinoctial wiggle to it, though, which is interesting. Okay, and so when I put them together, I see an equinoctial pattern. Okay, so where's that coming from? We have to explain that. Okay, and this is showing the same thing for the occurrence of large events, that also shows the Russell-McFerrin separation as we expect. Okay. So now, why do some indices show us an axial pattern? Because some do. And what they are is actually because indices like DST, which depend on the ring current, they have an inherent long response time. There's a smoothing in there. So what I've done here is I've just taken 1 hour data, okay, and it gives me the Russell-McFerrin pattern. If I take 6 hour averages, it's getting a bit elongated, but it's still Russell-McFerrin-ish. If I take 12 hour averages, then it's turned into the axial pattern. Okay, so this is exactly the same data. I've just changed the averaging time scale. And the ring current has an inherent response time that's longer than about 12 hours. And so the ring current indices like DST are going to show you an axial pattern. And it's really a Russell-McFerrin pattern that is just been averaged. Okay, so it's what this turns into when you average it over a long enough time, over more than 12 hours. So that solves the mystery of why some things looked like they were axial. DST does look axial, but right. So where does this equinoctial pattern come from? Okay, we know that the power input to the magnetosphere is behaving right, and the indices are responding to that with a Russell-McFerrin pattern, but there's also this tendency to have an equinoctial hourglass type effect. In other words, the tilt towards and away from the sun is having an effect. Okay. Now, the reason, if we look at the equinoctial pattern, these are indices like AM, but compiled from the stations that are within 3 hours of dawn, noon, dusk, and midnight. And you immediately notice the pattern around noon is pretty weak, where around midnight it's strong. And so this is coming from the night side, this equinoctial pattern. And so it's something to do with the tail here and not with the extraction of energy across the day side. So it's that energy is stored in the tail here as magnetic energy because the magnetic field is added to the tail. So the energy goes up. But there seems to be a difference between this configuration and this configuration, which is what we have at the equinoxes, whereas this is a solstice type configuration. Now, if we take a model of this, in fact, this is produced by a numerical model of the magnetosphere, and look at a cross section across the tail. Okay, so we're looking now back at the Earth from far down the tail, and this is what we see at the equinoxes. Okay, and this is what we see at the solstice. And this is the magnetic field. Magnetic field, the energy goes as the square of the magnetic field. If I look at the total energy, there's more energy stored in the tail here than there is here. So the tail is a better reservoir of the energy that's been extracted when it's like this than when it's like this. It's more likely to get rid of it again. And when it gets rid of it, that's when we get particles being shot back down to the Earth and we get enhanced aurora and a substorm and all the rest of it. That's more likely to happen when at the equinoxes than here because the tail can absorb more when it's in this configuration. Okay, so that begins to explain where the equinoctial pattern is coming from, because it's to do with the tilt towards away from the sun. It's not necessarily the tilt, it's the effect it has on the tail that matters. Okay, I need to hurry up. And I'll skip that. Okay, so there's some evidence that this is the case. Pardon me. The real evidence is that if we squeeze the tail more, we find with more dynamic pressure in the solar wind, again, that increases the energy stored. And what we find is that as we increase the dynamic pressure, so the amplitude of this pattern gets bigger. Okay, so this equinoctial pattern grows as we squeeze the tail, which gives us support for the idea that this is a separate mechanism. So the geomagnetic activity is part modulated by the Russell-McFerrin effect, and that will favor either By positive or By negative, giving you Positive gives you September, negative gives you March. But then the squeezing of the tail gives you this hourglass-like pattern because the tilt towards the sun starts to come into it. And you need both. To get geomagnetic activity, you need to extract energy, but then you need to get the tail to release it to come back to Earth. And so it's the combination of those two. So we can take some parts of the Russell McLaren, but the actual pattern looks like it's equinoctial. So it's a combination of the two, and that's really the mystery. Okay, so I'm just about out of time. So let me try and sum up with some key points, what I've been trying to tell you. So all this is about average activity, not the big events necessarily. Okay, and on average, the both auroral and geomagnetic activity peak at the equinoxes. And that's a known fact when we average over that time. The control of which equinox dominates, whether it's March or September, depends upon the Y component, the dawn to dusk component of the IMF. And that tells us that the Russell-McLaren effect is important, is a key to the energy transfer into the magnetosphere. But then this business of how well we can squeeze the tail and how much energy we can store in the tail before it's got to give us a substorm, then that depends on the tilt towards the sun, and that gives us the, sorry, I've jumped ahead. That gives us the equinoctial form, okay, where the dipole tilt towards and away from the sun comes. It's not to do with energy transfer into the magnetosphere, it's to do with how much we can store before we get an auroral explosion. Okay, so that's the origin of the equinoctial pattern. The axial pattern is actually just the Russell-McLaren pattern that's been averaged over 12 hours or so. Okay, so we've got an explanation of why there were three different patterns in different indices and things like that. Okay, I think I've just about used my 45 minutes, so I'll stop there. That's an awful lot, and that's sort of research level stuff I've been talking to you. I've given the PowerPoint display to Mary Beth and Tanya.
Yeah.
And so if you'd really like to look over it again, I'm sure they'll pass it on to you.
Yes.
And you're welcome to do so. I'm very happy to take any questions. I was expecting to be interrupted and answer them as I went. So I've left myself with some questions and all that, but I better answer other people's first.
All right. I'm just looking, I'm scanning through because I didn't do the greatest job of like watching the chat while sitting here because I'm
No,
listening to you too.
but
So let's see. Let's see if there's anything. I mean, it's
Yeah,
go ahead, Tanya.
there is a great comment in the chat that Steve is saying that he used to think about the magnetotail as a rubber band stretch, but now he feels that it's more analogous to an electrical capacitor.
Mhm.
Yeah.
That's actually a reasonable point. Yes. I think it's a bit also like a balloon. You know, you can put air in it, and the more you squeeze it, the more the energy goes up, and it's more likely to burst and deposit the energy in the ionosphere and thermosphere on the night side. Um, but yeah, there are various ways of thinking about it. But yes, it is. It's the storage and release system, and the equinoctial pattern, if you like, is a signal of the storage and release pattern, which is part of the story. But you've got to get the energy in there in the first place, and that's the Russell-McLaren pattern. But if you don't get the energy in, then it won't happen. And that's why even the equinoctial pattern will split into March or September, depending on the polarity of BY. So that tells you that it's the combination of the two that's at work there. But
Oh,
it's a good way of thinking of it.
yeah, that was really cool. I mean, I actually going way back to the beginning. I didn't even think like, the how the magnetic pole moved because I always thought it would I always thought like Aurora would move based on that, and it's interesting that it didn't affect North America that much,
No.
but Europe was drastically different.
Yeah, yeah, yes, I know. It's remarkable. And we have I mean I Lockwood is a town in Yorkshire, and my father came from near there, and his father used to talk about seeing the aurora, and I thought, yes, yes. He'd had too many drinks down the pub and he's seeing it on the way home, isn't he? But actually, he probably did. It was more common, and it moved. I mean, John Dalton took all his measurements in the Lake District. He studied the aurora enormously. In fact, the Dalton minimum in sunspot number comes from the fact that he didn't see many aurora, and he was in Kendal in the Lake District. So it moved over the centuries northward. So
Yeah, that's wild. Yeah,
yeah.
until you put that.
Plymouth,
Yeah.
right
Well,
back in the early 17th century, there was a doctor called Huxham, wrote a absolutely vital book on fevers but he was a terrible doctor. All his patients died,
oh
but
no.
he seems to have spent most of his time chronicling the weather and the aurora. So, but yeah, he was a very dodgy doctor indeed.
But he
But
has
yeah, a
Aurora record.
theoretician, obviously.
That's fascinating. Yeah, it's yeah, yeah. I mean, I guess there's not really any questions to go over. I'm guessing people are just absorbing it because it's a lot to absorb.
Yeah. Well,
But
Yeah.
well,
yeah.
there are a few questions.
Mhm.
As you know, our chasers kind of work with live data, and yes, it's not perfect, and we're kind of trying to decide when is the best aurora going to be coming. And we look at IMF, obviously. We also look at least quite a few people look at solar wind and density. And
Mhm.
there is a belief that I don't know to what degree it actually is kind of confirmed by science that when we have big events and we see high speed and high density, that's preferable to sort of slower speed, um, as opposed to sort of like, well, how much really is IMF playing into picture for aurora as opposed to solar wind and density? So
Okay.
how do those two things, the magnetic side and plasma speed and density, play together to determine substorms?
Right. Okay. It's a very
Yeah.
good question. Let me go right back and get this equation. I'm not going to worry people too much about it, but this is the solar wind number density, and this is the mean iron mass. So, and these coefficients all fall out of that simple idea that it's the energy density in the solar wind times the area, which we get from the compression of the day side, and this transfer function, which is the fraction of the energy, and then we build terms for those, put it all together. So what do we have here? We have the strength of the IMF here. We have the solar wind number density. We have the solar wind speed, quite a big dependence on the solar wind speed. V crops up a lot. And then this is the IMF orientation. Is it southward or northward? Okay, that's where that comes in through this term. So all of those things matter to how much energy we're extracting from the magnetosphere. So high velocity, high density, and southward IMF all combine. The perfect storm is when you get all of them, okay? And but then you can have high solar wind speed and density and high field, but if the field is northward, this term goes towards zero, okay? So it is important, but it's like a controlling factor, okay? How much of this are we going to extract? So that's the part relevant to the Russell-McLaren effect, where we're talking about how much energy goes into the magnetosphere. And if I just remind you somewhere, okay, so this is that power calculated from solar wind parameters. as a function of in the FUT plots, and this is the model Russell-McFerrin pattern, and you can see it's really good. Okay, so that power input to the magnetosphere is following the Russell-McFerrin, and it has this split according to BY. But then the other part that comes in is this business of the equinoctial pattern and how much can the tail take before it explodes and gives us a big event. Okay, and it releases all the energy that it's stored up, and that depends on the solar wind dynamic pressure, and that is the solar wind density times the speed squared. Okay, so again, it's coming in, the density and the speed are coming in. They're a factor that helps. Okay, so it does contribute to, so the Russell-McFerrin effect and the transfer of energy into the magnetosphere builds the tail up. The tail gets more and more magnetic field in it, but the squeezing of the tail by the solar dynamic pressure helps the release, and it's that that gives us the equinoctial pattern. Okay, so the density and the speed are contributing to both parts of this, the extraction of the energy and storage in the tail, but then the extraction, the depositing of that energy down into our ionosphere and thermosphere, but in different ways. Okay, so that's why the response is quite often quite difficult to unpick because the two things are happening. Okay,
Okay,
so
that makes
yes, they matter, but none of them. The IMF orientation on its own is not the factor. The solar wind density on its own is not the factor, and the speed is not the factor on its own. They all contribute. Does that help?
yeah,
Yes,
yeah, actually.
absolutely. And sort of follow-up question to that, with the energy stored in the magnetotail, when it finally releases it, how much of that energy is released? Because again,
Oh,
there is a lot of talk about there is preconditioning, so not
yeah,
all the energy is released.
yeah,
And sometimes we see big storms and they subside, and then something else comes along, and the expectation is that it's going to be stronger compared to sort of that same event coming
yeah.
on its own. And that's not two events running together. They're separated by fairly calm period. So is there that stored energy, and how long, and sort of
Yeah.
what triggers its release?
The answer is that's an unbelievably good question. I believe the answer is that a substorm does not clear all the stored energy. Okay. There's a wonderful plot by John Wygant, and it was published in about 1983. John Wygant was at Berkeley, and what he did was he looked at it doesn't matter. It's an index of activity as a function of time since the IMF turned back northward. Okay. And what you find is in the first hour, you might get quite a lot of activity. So this is the stored energy that's been built up before the IMF turned northward. But as you went on, of course, you get less and less data because the IMF doesn't stay northward for, it's going to flip back southward after a while, but he got some periods that were 9, 10 hours long. And what he found was you got less and less substorms and they got weaker and weaker as you went on. Okay, so an hour after you'd had southward IMF, you might get the tail releasing a whole load of energy. 2 hours after, not much, much considerably less, and it fell off exponentially by 9 hours there's almost no effect. Okay. But in that 9 hours, you'd probably had 4 or 5 substorms. So turn it northward and keep it northward. Doesn't happen that often, but if it does happen, if you've built up the tail, it seems to me to take 4 or 5 substorms, getting ever weaker before you actually get back to a base level.
Okay.
So I think the answer is that the energy built up in a substorm growth phase, when the tail is getting fatter and you're stuffing field into the tail, that is deposited in the thermosphere and ionosphere. I'd say about 3/4 of it, but there's a quarter left over to power a next substorm, a weaker one and a weaker one. So So that I think that was an incredibly useful paper. And it's interesting that other people don't seem to have noticed it, but I think it's really insightful. It told me a lot anyway.
Yeah, send us a reference. We can definitely post it in the video description if people want to read it.
Yeah, it was the S33 satellite, and what he was actually looking at was the voltage across the polar cap, what's called the transpolar, the cross cap potential. Being a bit of a pedant and English, I do object to that actually because it's not a potential at all. It's a potential difference. It's a voltage. I use the term transpolar voltage, but the literature will always talk about the cross-cap potential. Well, no, it's a potential difference. It's the difference in voltage potential between dawn and dusk, and he was looking at that as measured by spacecraft, but that's a useful indicator of how much uh, energy is being stored in the tail.
All right. Well, one
Yeah.
just popped up. Is there an upper limit to the energy the magnetosphere can store?
Ooh. um, there must be practically, um, uh, because well, that's an interesting question. Um, it would be quite nice to take a numerical model and just see what the maximum is. If
Yeah,
you shut off all mechanisms that, if you could stop the tail reconnecting and so that the field just grew and grew and grew, then what would happen? The magnets would get very fat to start with. It would
yeah.
turn, it would grow in diameter. Um, there probably is a practical limit, but I wouldn't like to say what it was.
Right. Yeah, because it's always being shed off, basically.
Yeah, I'm quite
Okay.
sure that because I mean, as the tail gets fatter and fatter, the squeezing effect of the solar wind gets larger, so that actually helps you store more. But yeah, I can't answer that, but it's a good question.
Yeah,
Makes me think. It
fair
makes me
enough.
think a numerical model run on that would be worthwhile.
If anything, it would be interesting to
Yeah.
like. So that's yeah.
And from sort of practical observations, it takes about an hour from southward turning of the IMF
Yeah.
once it hits the magnetosphere to really build up that first substorm.
Yep. Yep.
Where does that timing coming from?
Okay. I can go back to one of my slides early on. Okay. It's really this. If I run this again. So the field line comes. Okay, southward IMF starts to get draped over. Okay, I don't really carry it on, but this field line is going to end up looking like the one in the tail. Okay, it's going to become an open field line in the tail. It's going to get so draped that, okay, so as this moves on, so I've only done this to cover the day side, but it will move right on over here to the right. And sorry, you can't see that, right over here to the right. And by then it will be one of these field lines here that's in the tail. So that time scale is really the time to move from here along here so that the field line starts to get draped into the appended to the tail, okay? And then the magnetic pressure goes up here, that starts to squeeze the cross-tail current sheet here, and you're more likely to get a reconnection burst that starts taking that energy. The field lines snap back towards Earth, and that energy is deposited as in the upper atmosphere. Okay, so it's really the time for field lines to get appended to the tail. Okay, so as the solar field lines get appended to the tail, that takes time. They've got to travel along. Okay.
Okay.
And that's about an hour time scale, 40 minutes to an hour normally. But after about 40 minutes, the tail here says I've had enough and gives you a
Yeah.
reconnection event that deposits a whole lot of energy down here.
And that's true for isolated substorm, but we often well, not often, but sometimes we do have big events that IMF is southward for hours. And then we get really strange things with the substorms that are sort of there's aurora going on,
Yeah,
but there are also stronger substorms every 3 hours. So we've known them as sawtooth events, and we've seen
yeah,
a
yeah,
beautiful one, just gorgeous one on October 10th, 11th. That was a
yeah.
sawtooth event with IMF, I think, minus 30 nanotesla south.
Yeah, no, the energy is being piled so rapidly into the tail that it keeps trying with an event to, but that doesn't actually solve the problem and a whole load, so that you just get one after substorm expansion after another with no growth phase in between. So yeah, that's exactly right. Can I show you something actually?
Yeah.
Just this is not entirely relevant, but I can't resist it while we're talking about things. This is a movie that was made by a colleague of mine. I left it in the spares because I knew I was going to run short. This is actually, these are we published in real time on the web. Um, um, you can also download the software. There's a GitHub that lets you download everything. This is a set of predictions that was made ahead of the March 10th event. So it's a movie. So if I run this, so what you're looking at here is the sun is here. That's the Earth. There's probably stereo A and B. One of them is Venus, and I guess that might be Mars. I don't know, but whatever. They're various. Oh yeah, here we are, Mercury. Um, um, and this is the normal Parker spiral configuration. What you're seeing colored is the solar wind speed. Now, this is not a full MHD model. It's a ballistic model, kinetic model only. And that has the advantage that we can run it incredibly fast. So in the propagation time from the sun to the earth, you can run Enlil or a full MHD model about 4 times. All right. We can run this 4 million times. Okay. Um, and these were the predictions made for May. So that's a CME, misses the Earth, but that's what hit Earth. Now we knew that was coming. We'd made that prediction before it actually hit, so we knew we were in for something special. Um, what's great about these predictions is that we can use data assimilation. So any data we get from any of the like Messenger or ACE or what have you, we can go back rerun it again to make the predictions fit the data. Okay, so it's called data assimilation, and we can do it in real time. We can also make thousands and thousands of runs before the thing arrives, and that gives us we each of those runs we perturb an unknown just a little bit, and so we get a distribution. And this is like your weather forecast. When you get the probability of rain, it's because they've done an ensemble of predictions. And what they're saying is 90% of them give you rain. And so you've got a 90% probability of rain. We have the same thing with this. We can put probabilities on events happening because we model all this. It's not self-consistent. The magnetic field is just frozen in. And so the plasma just goes. We don't apply any magnetic pressure because that would take an MHD model. We just let the packets of solar wind go and drag the field with it. And we start off from magnetograph data on the sun so that we've got the magnetic field there. But as I say, that prediction was available to us the day before the March event hit. So we were looking at it thinking, oh my goodness, this is going to be fun. These forecasts are available in real time, the whole time, continuously. So it's called program's called HuxT, and it's the GitHub and the server is on at the University of Reading. So I don't have a web page for it, but
We
Oh,
love
we know it
Chat,
and love
chat,
it.
Chat GPT will find it for you.
it. Yeah.
Yes. it will then lie about what it can do, but
Right.
it'll
But
find it
you
for you.
know, yeah, it's fun seeing that again because I often forget. I'm like, that was a pile up of CMEs. That's for
It
sure.
was, wasn't it? It's just astonishing. Just
Yeah.
astonishing. Yeah.
So
Yes.
it's fun. It's a fun to relive again. We need
And
to
has no relevance to the Russell McFerrin effect. That would
celebrate.
have caused those events, whatever time of year it came on, because in those CMEs and in the sheaths ahead of those CMEs was an awful lot of southward pointing field,
Right,
and they're fast, and so there was lots of energy to extract, and the southward field meant that we could extract it, and oh yeah, that's the actual data when it hit. Um, but yeah, so we fold in all this remote sensing data and things, and we keep modeling it in real time, and we use heliographic images, so we keep modeling those on a continuous basis. So in the way that the weather forecasts are always updating, it's a running forecast the whole time, updated by what's happened. That's what we're doing here. It's called data assimilation. But we can only do it because the model is so simple and
right.
therefore
Yep.
fast. So you can run it on your computer, on a laptop, by the way. It really
Wow.
doesn't demand a lot. But yeah, it's just a different philosophy from
Right,
an MHD model, which is going to be fully correct, but it's awfully slow. So.
right. And then when you're in the business of trying to forecast stuff, speed is everything.
Yeah, yeah. You
So
couldn't do data assimilation by the time you've got a forecast. You can't go back and set it, run it again. I mean,
yeah,
to do data assimilation, we're doing it, we're rerunning it um, every every few seconds so that we can keep assimilating the latest data all the time. So, yeah.
love it. Well,
I couldn't
Todd,
resist showing you that. Bit of
no,
a bit of
it,
advertising for my colleagues Matt and Luke, who do put a lot of work into it.
we always appreciate it. We do because it's one of our in this aurora chasing world. It's one of our favorites to go to.
Oh
So
yeah, yeah, yeah.
yeah,
As I say, I think it was the third most extensive auroral event ever. Okay.
yeah.
So
I know that was a cool chart too to see that, you know, because everybody talks about the Halloween event too in
yeah,
2003.
yeah, yeah,
Comparing
yeah.
that, to the one, actually the one I was surprised by was what the 1872? Is that what we said it was?
Yeah, yeah. I like to call it. I got into a bit of a row about it. Oh, incidentally, that was last year
Yeah,
in Aurora. So that's the May event. That's a pretty damn good one in October too. It was
yeah,
Hmm.
August. And then just at the end of the year on New Year's Eve, it gave us another one. And these are the occurrence probabilities going right back to 1650. And this is the bite out because of sunlight, basically, in the Northern
yeah,
Hemisphere. And then these were the geomagnetic, this was the AA index. And you can see that again, the geomagnetic system is going well into the 3 or 4 sigma range. So that's 99.99%
it
percentile. So that's,
was awesome.
yeah, yeah. Where was that plot? So that was just for last year, but
Yeah, it's kind of at the beginning. There it is.
there it is. Yeah, yeah.
Hmm.
Yeah, that's the Carrington. That's what I call the Secchi event.
Yeah,
Secchi did a lot of work on like disruption to telegraph
yeah,
networks and things. He studied that. So he studied the space weather associated with that event. Um, yes, there we are. 2003 Halloween events. That's going to be around there.
yeah.
So big, but not, unusual. Bastille Day event is it that? No, it's not. It was 2000, wasn't it? Bastille event was strange because although very low latitude aurora was seen from space, by coincidence we seem to have cloud everywhere that mattered,
Oh,
and
yeah.
it wasn't seen that well from the ground.
That pesky terrestrial weather.
Yeah, 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 boring, isn't it? Yeah,
Yeah.
yeah, I know. But no, it's quite interesting. So I can't remember which one that is.
Yeah, I heard there was a couple like in the 50s. I remember.
There were 58, I think, IGY. There were a couple of storms. And I've just done a couple of papers on. these two, there are two here, and they're called the Fatima storms because it was to do with a prophecy made by, I think, a nun called Fatima.
Okay.
So that they got labeled the Fatima storms for well, for that reason. And but they're really interesting because they're very similar, but one of them appears to have come from a CME that was right on the limb of the sun. So we don't normally, when we're doing forecasting
Right.
nowadays, we ignore ones that are right on the limb of the sun, but it looks like this came from. And the other thing that was interesting was they hit at completely different universal times, about 12 hours apart. They were only a couple of weeks apart in time, but they were also different in their universal times by about 12 hours. And that meant that the low latitude aurora in one case was all in the Atlantic basin, so the east coast of America and Europe. The other one was Japan, New Zealand, and the west coast of America. So it shifted where the low latitude aurora happened by 12 hours because the impact was 12 hours different.
Oh,
So the actual time of impact changes your chances of seeing aurora.
yeah, yeah. We've run into that a couple times.
Yeah, 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 yes, yes. Or in Japan, they're all seeing nice low latitude aurora, and it's all fizzled out by the time it comes round to us. Yeah,
Yeah, like wah wah.
yeah, yeah.
Cool.
Oh, this, by the way, was the Dalton minimum. So,
Okay.
Oh,
and in fact, one of my locations in yellow here was Kendall.
Mm,
So John Dalton was making his measurements at Kendall, which has come down. No, that's not right. That can't be right. Oh no, yes, that's right. Yes, yes, it's come equatorward of the aurora. But yeah, he noticed there weren't many aurora here, and that's where the Dalton minimum came from, was observations of aurora.
interesting.
It
Yeah.
is, yeah. The data are probably not that reliable around here. There are probably some huge events in here that just never
Right.
got reported. But you can only report what was reported. So
This is true.
yeah.
Yeah.
And these were all the stations that were operated up near the pole in Greenland and things like that.
Okay.
That's why you get the lines. But then you can see where financial cuts hit and they were all closed down. So
Yeah, that's such a bummer.
yeah, yeah, yeah. This is Svalbard up here. So
Okay. Very
there we
cool.
go. Yeah.
Well, I think do you got anything else, Tanya? Okay. I think we're all caught up then.
I'm also happy if anybody wants to email me and ask questions, and I'll
Oh
try
yeah.
to answer them.
oh,
People,
thank you so much. Much appreciated.
yes, and there you got
Pleasure.
lots of thanks in the chat too. So everybody's appreciative of you coming on here and explaining some of these things to us.
Yeah.
So it's I always learn something and it's fascinating. So
Yes. Yes.
thank you so much. Yay.
You're more than welcome. It's been a pleasure.
Yes. All right. Well, I will end it on the YouTube and give everybody their time back. So
Good.
until next time, thanks for watching.
I
All
have other talks I can give about Aurora, but
right. Yes.
I'll let
All
you
right.
have a rest first.